Hello, everyone. Thank you for being here today and for your willingness to join this webinar on smart healthcare in the Internet of Things continuum. I will say a few words about MDPI first, and then we will continue with the next content. A pioneer in Scholarity, open access publishing, MDPI has supported academic communities since 1996. Based in Basel, MDPI has the mission to foster open scientific exchange in all forms and across all disciplines. Our 496 diverse and open access journals, including 487 peer-reviewed journals and 9 conference journals, are supported by more than 295,000 academic experts who share the same mission, values, and commitment to providing high-quality service for our authors. The sponsor of this webinar is Censors Journal. Censors is an international peer-reviewed and open-access journal which provides an advanced forum for the science and technology of sensors and its applications. Censors is published semi-monthly online by MDPI. I would like to present you the upcoming conference that Censors Journal will organize in 2026. That is the 3rd International Conference on AI Sensors and Transducers, and this conference will be organized in Korea. The organizers will be Censors Journals, Micro Machines Journals, AI Sensors, Micro and Remote Sensing Journals. Please feel free to check this conference, to check more information, and to let us know if you would like to participate. Our conference chairs are announced, and also planetary speakers and steering committee. Here is today's program. At first, our webinar's chair, Dr. Claudia Zavaglia, will open this webinar with few welcoming words. Then we will have 2 speakers. At first, Dr. Luca Greco, who will present the topic on user-centric platforms for continuous healthcare, the Entrust project. And then second speaker will be Dr. Raffaele Gravina, who will present the topic on frameworks for continuum computing wearable systems, the CocoWear project. Then we will have 1 question and answer session, after which our chair will conclude and close this webinar. If you're interested in submitting your research to a section that is linked to this topic, please feel free to check Internet of Things section in Censors Journal. And if you have any questions for our speakers, please post them in question and answer box at the bottom of your screen. But please remember to add the name of person to whom you would like to address your question. I would like to introduce our webinar's chair, Dr. Claudia Zavaglia. Dr. Zavaglia is an associate professor of computer engineering at the University of Calabria in Italy. He holds a PhD in computer engineering and has established strong international collaborations with leading institutions in USA and Spain. Dr. Zavaglia has been an IEEE member since 2016, and with over 90 scientific publications and active involvement in multiple research projects, his work focuses on digital twins, Internet of Things, and edge computing. Dr. Zavaglia, please feel free to share your screen and to say a few welcoming words from your side.
Okay, thank you very much for the nice introduction and for having organized this webinar. Good morning, or also good afternoon or evening to everyone. I saw that a lot of people in the audience has different surnames, so maybe we are not on the same time zone. So simply hello, and thank you for being here attending this webinar that is focused on the topic, a really hot topic nowadays, that is the smart healthcare in the Internet of Things continuum. And of course, I would like to start thanking the other two speakers that I will introduce you soon. So in the next few minutes, I would like to walk you through the context and the motivation behind this seminar, which are some key technological directions and the main challenges that still remain open in the fields of healthcare. So first of all, let's start by providing some words about the context, the research context, in order to facilitate the webinar also to audience who maybe is not really focused in this topic. So in recent year, we have experienced the progressive evolution of our world into a smart ecosystem. Why? Because we could nowadays see that in our life, there is an increasing number of smart devices and smart systems that start to interact seamlessly with each other. So this is what it is typically defined as an ecosystem. And such an approach is also impacting the healthcare. Indeed, in the last year, we have seen conventional healthcare solutions and healthcare devices that have been deeply impacted by technology. In particular, we have seen traditional solutions that have been augmented by new technology, but also new solutions developed from scratch that have been enabled by the technology. And in particular, a relevant role has been played by the ICT, information and communication technology, and also in particular to the Internet of Things one. I would like to say that Internet of Things is not the only enabler, but it is better to discuss about in general of ICT technology, because as we will see next, Internet of Things is a first building blocks, but all the advanced smart healthcare system we will delve into later also exploit other communication and information technology paradigms, such as cloud computing, edge computing, artificial intelligence, big data, and so on and so forth. So smart healthcare is based on many technologies and paradigms. But of course, IoT, due to its pervasiveness, play a fundamental role. What do we intend for Internet of Things? For Internet of Things, we intend all that set of devices, typically everyday devices, that are augmented with communication, data processing, sensing, and actuation skill. So basically, through the Internet of Things, devices could be able to sense the environment in which they are, to process the data they acquire through this environment, and also to share this data or to start and trigger actuation. Obviously, supported by communication technologies and paradigms such as the power of the cloud, the power of the AI, the power of big data. All these pieces together contributes to create an ecosystem in which advanced solution could rise up. And this holds also, obviously, for the healthcare scenario, in which some buzzwords or keywords, depend of your expertise, are nowadays very popular, smart healthcare, healthcare 4.0, Internet of Medical Things, and so on and so forth. What do they have in common is that they rely on ICT and especially on IoT technology. So why this transition towards smart healthcare is nowadays so pressing and so crucial? The answer lies in a combination of demographic, medical, and systemic pressures. First of all, we know that the world population is not only continuously aging, but it is also growing in absolute number. And so this means that elderly individuals need constantly long-term monitoring, early intervention, and also there is a growing incidence of chronic diseases. So there is the need of constant attention, frequent checkup, and personalized care pathways. But on the other side, there is an increasing pressure on the healthcare system that is not balanced by the availability of human and financial resources. Because if on the one side the demand is increasing with more patients, more procedures, more long-term condition, on the other side there is often an insufficient or declining availability of medical staff and budget. So this imbalance highlights a very clear need. We must find new ways to extend the reach of healthcare, and this could be done only by using technology. So this led us to the desiderata, so the desired properties of the next generation of healthcare solution we would like to experience. We need, first of all, to provide clinicians with new and valuable support to assist the patients. And in the other hand, we simultaneously need new instruments to directly, without the need of the doctor, assist patients. So we need systems that are decentralized so that the monitoring of the patients can happen closer directly to the patients wherever they are. And we need solutions that are context aware, so capable of understanding the specific patient information, the specific patient need. So we need a customized healthcare. And we need, obviously, to do this assistance continuously and in some cases also remotely. And this is something crucial, for example, if we think about rural environment in which it is still sometimes not possible to reach hospital or to reach doctors. So in summary, what do we need is a technology that could assist doctor and offer high quality proactive support to the patients. But this scenario I have depicted is not unrealistic or futuristic. It is something already implemented and developed in our life and in our time. And here in the slides, I have reported some screenshots about some already ongoing and developed smart healthcare systems that could provide the support for different medical situations. For example, through AI, it is possible to quantitatively assess and quantify pain. And this is something really useful, for example, in the case of baby or in the case of elderly patients affected by dementia. Other kind of use cases may be, for example, related to diabetic patients, in which, for example, smart pens and smart insulin pump can operate upon these patients, and even without the need of the smartphone or the doctor. Other examples are some wearable gadgets like the earrings that could be used to measure the blood flow at your head. Or we can have a lot of, for example, images processing techniques that could be successfully applied to recognize cancers or other kind of disease. Or we have seen a lot of examples during the COVID pandemic of IoT solution that was able to evaluate the severity of some disease before the patients actually become critical and directly at his or her home. Okay, so this is just for saying that smart healthcare is already between us. Maybe not everywhere, maybe in few test beds, but it is something that could be actually realized on wide city in a few years. But obviously, there are, besides the potentials, also some important research challenges, because as any transformative domain, also smart healthcare still has some open issue. Some of them are organizational, and we will not deal with them today. It is important to establish a good and fruitful interaction between technician and doctor. There is the need to fill some infrastructural gaps, so to provide the hospital with advanced device and instruments. There is the need of personnel that is skilled in an interdisciplinary way to manage this device. And also, obviously, such device should be compliant to all the regulation that feature the healthcare domain. And so we will not deal with this organizational issue. But today we will mostly delve into some ethical and technological research challenges. The data treated by smart healthcare systems are typically sensitive data. So we need to collect as much data as possible, but in a privacy-preserving way. We need to pool this data in order to train artificial intelligence model, but we would also try to keep the privacy and protect against data leaks. We need explainability, because no one would trust in a black box, and we need trust in this. And then we have technological issue, because obviously IoT devices are featured by a scarcity of resources, but at the same time, despite this limitation, we would like having a real-time and customized medicine, and we would like to have devices which should be interoperable, but also accurate and able to scale. So there are still a lot of room for researches. And exactly trying to fill some of this research gap, today we will see the experience of two research projects that have been both funded by the European Union and by the Italian Minister of University and Research. And so this gives me the chance to introduce our two invited speakers. They are both associate professor, and in particular, Dr. Luca Greco is associate professor at University of Salerno, Italy, and he is the principal investigator of the Entrust project, while Dr. Raffaele Gravina is associate professor at University of Calabria, and he is the principal investigator of the COCOWARES project. They both, just for the sake of time, let me put in common your skills. They are both very experienced, and they have co-authored dozens of international journals. They have served in many roles for conferences, for editorial role, and they both focused their research on computer engineering, and with a particular, let's say, emphasis on smart healthcare, wearables, Internet of Medical Things, and so on and so on. So I would like to pass the floor initially to Dr. Luca Greco and then to Dr. Raffaele Gravina, and as anticipated, there will be the question time in approximately 35-40 minutes for now. So please, Luca, the stage is yours.
Thank you, Claudio. Thank you. I would like to share my screen first. Claudio, thank you for your kind presentation, and thanks everyone for participating to this webinar. I am Luca Greco. I am from the University of Salerno, Department of Information and Electrical Engineering and Applied Mathematics. And today I'm here to illustrate the Entrust project, which is user-centric platforms for continuous healthcare. The presentation is organized as follows. We're going to start by giving some information about the project itself, and then I'm going to move to the motivations behind our work, some little background aspects about the enabling technologies, and then I'm going to illustrate the Entrust architecture. Finally, I would like to explain something about our case study, which is the Entrust Hub. And I'm going to draw out some key takeaways and future directions. So let's start. About the Entrust project is a PRIN project. PRIN stands for Research Project of National Interest, and it is supported, as Claudio said before, by the Ministry of University and Research here in Italy, and together with the European Commission through the National Recovery and Resilience Plan. There are two research units involved in this project, the University of Salerno, with me being the principal investigator, and the University of Calabria with Dr. Savaglio being the co-principal investigator. The project belongs to the Health Cluster mission, which aims to improve citizens' health and well-being by developing innovative health technologies and monitoring and treating diseases in order to mitigate health risk. Let's come to motivations. As Dr. Savaglio was extensively discussing before, with a few exceptions, almost every area of the globe is experiencing a rapid aging population, which means that we have a strong rise in chronic diseases, and this together with frequent epidemic outbreaks and increased pollution leads to a strong demand for a novel approach to health management. And our idea with the Entrust project is to provide an integrated edge cloud platform for continuous monitoring by leveraging Internet of Things technologies due to their intrinsic, transparent, and non-invasive nature. We want to improve life quality through real-time health control. For those of you who are familiar with edge cloud computing, some background about this enabling technology. First, most approaches rely on a 2 or 3 layered sense and forward architecture, which means that we have some sensors, let's say wearable or field sensors. Data from sensors are gathered and are obtained, are collected by edge devices, and in most cases, those edge devices are in charge of pre-processed data, are in charge of, I'll say, filtered data, and filtered data are then sent to fog servers, if available, or cloud servers to do how to say, some deeper processing. In the healthcare domain, we will be interested, for example, in revealing critical conditions for the patients, so we can elaborate on those data, which are obtained from sensors, and by employing, let's say, some machine learning techniques, we can investigate if there are anomalies in such data. But there are some issues. We want to deal with healthcare domain, so we want to realize a real-time monitoring. We want to deal with mobility. We want to deal with location transparency. We want to preserve privacy because we are not willing to share, I'll say, some confidential or data belonging to patient throughout the network. So we have real-time constraints because we want notifications to be evident to the patient in time. If we deal with the cloud architecture, we know that there are some bandwidth constraints. If we deal with the edge level architecture, there are some limitations because if we want to process data at the edge level, we should face, I'll say, tiny device resources, constrained device resources that could be not performing for data analysis or prediction. So a promising trend in the last 5-6 years is to move the AI to the edge. How to say, we want to enable a seamless edge cloud cooperation by means of edge intelligence. That means that we want to perform elaborations as close as possible to sensor as to the patient. Our Entrust proposal falls in this context. So we want to propose a user-centered platform for continuous health monitoring, even in mobility. See that when we talk about user-centered platform, we are talking about an ecosystems of sensors, of devices, of edge devices, of fog devices or cloud services. So we want to identify a particular architecture that allows to treat this problem in an easy way. For example, our main features comprises a fluid architecture which relies on two meta layers. I'll say we can call them local layer or remote layer. And we also identified a number of multi-protocol gateways for interoperability. As methodology, we stressed patient-centered design because we are interested in solving patient problems and monitoring patient status, health status. And we also emphasize a simulation-based design because we strongly believe that simulation can help in designing edge devices, for example. So the entire focus is about two fundamental aspects. On one side, we have architecture. On the other side, we have simulation. And we also had the chance to go deeper in the algorithm optimization process, which means that if we want to use, I'll say, algorithms that were designed for a cloud service, we want to adapt those algorithms in order to use them in an edge context. So the high-level goal of the Entrust monitoring can be viewed according to different directions. What we want to measure? We are interested in dynamic monitoring. We want to monitor patient dynamically, so we want to gather information from wearable sensors, information or data such as heart rate, ECG signals, oxygen saturation, or glucose level. If we are in a constrained setting, such as monitoring at a room level or in a clinical setting, we can also leverage data from field sensors, such as air quality monitoring, temperature, humidity, and so on, pollution levels. Why? Because we are interested in addressing diseases, even chronic diseases in domains such as neurological diseases, cardiovascular diseases, or problem that deals with ambient assisted living. When we would like to apply this kind of monitoring continuously, if possible, and in indoor settings or in mobility. We would like to use edge intelligence as a particular enabled, and we are interested in propose a fluid architecture that will be designed according to patient-centered and simulation-based procedures. So the Entrust architecture is basically made of two layers. Is a two-layer design. We have the local layer and the remote layer that have to cooperate seamlessly. At the local layer, we have wearable sensors or wearable devices, carryable devices, and some local gateways that can change according to the context. For example, if we are in mobility, we should have mostly wearable devices. If we are implementing a monitoring in a constrained setting, such as at room level or clinical settings, we could leverage also fog servers or multiple instances of edge devices that can cooperate together. We can also leverage a remote layer. A remote layer comprises internet-based resources, for example, for storage data from our edge devices or for doing the heavy processing. The idea is to leverage a dynamic classification based on user proximity, which means that a user which is close to some kind of services can leverage those services. We also investigated different gateways for our project, for example, microcontrollers, single-board computers, smartphones, and according to these devices, we have different functionalities or services. We could have internet connectivity, we could have multiple radio interfaces, we could track services or requirements, or implementing lightweight middleware for device discovery and task dispatching. As I was saying before, we strongly believe that simulation phase is essential for a correct design because a simulation allows us to evaluate resource needs in terms of computation, in terms of communication, or energy management. So we did a study in the first milestone of our project, which is the analysis phase, where we evaluated different simulators. For example, we selected the EdgeSim simulator, which is an application written in Java, and we could also use this simulator for expand some of the functionalities according to our needs. We believe that this kind of tools can generate deployment settings for our gateways, and we think that it's quite mandatory before new service deployment. So let's come to our case study. For this case study, I would like to illustrate the case of the Entrust Hub. Entrust Hub is an architecture which runs on a Raspberry Pi single-board computer with a modular containerized microservices, and we called it EdgeFirst Cloudburst because it can have two modalities. The idea is to gather data from wearable sensors, for example, ECG sensors, heart rate, breath rate, and so on. Those wearable sensors can send data via Bluetooth Low Energy or Wi-Fi to the edge node, which is our Entrust Hub. And the Entrust Hub could implement immediate processing by means of function as a service implementations. During our analysis phase, we evaluate different paradigms, and our focus came on the function as a service paradigm because in this kind of project, we want to, for example, implement the same behavior, the same function with the different level of depth at different levels. For example, we want to implement the anomaly detection at the edge level. We could implement a function that can run at the edge level, but with a lightweight model. If we can leave the stage to a different processing environment, for example, a fog server, we can implement the same function at the fog level with a different modality, for example, with a more accurate, how to say, model, machine learning model. If we need more computational power, the same function can be implemented at the cloud level. Within this architecture, we also utilized a containerized MQTT broker, which is a local broker which has been implemented within the Entrust Hub. And it is in charge of ensuring fast and secure communication between the different modules. For example, it can interface with the wearable sensors, and we can transfer the data by on the Wi-Fi network with MQTT protocol. Okay, so we also implemented a web application that manages, for example, the touch screen user interface within our architecture, and then some system logic by means of other embedded services. The Entrust Hub also has an InfluxDB instance as a microservice, and these InfluxDB instances handles local time series storage and enable fast queries and fully offline capable operations. So this kind of hub is also capable to work without internet connection in the local area network. As I was saying before, we have on-device analytics, which means that we can run some lightweight models, such as lightweight ECG classification at the edge level, without have to communicate with the fog or the cloud level. So the idea is that the edge level is able to process data coming from the sensors and can notify patients with anomaly detections. So the idea is to leverage, for example, lightweight ECG classification with the binary performance. We can update our status by giving patient notification about normal behavior and abnormal behavior. This can be done at the edge level. All components have been deployed as Docker containers. This guarantees further deployments, and we can also create a unified edge platform for rooms, hospital rooms, or constrained settings. Being local, the system delivers low latency, high reliability, and strong data control, because all the data are actually stored within the InfluxDB instance, and we could also leverage cloud services of storage if necessary. In our first idea, we use a single, for example, instance of the Entrust Hub, so the function can be implemented by means of a simple fast API as a containerized service. But if we deal with constraint settings, if we deal with clinical environment, we could also try to use different instances of the Entrust Hubs. Okay, and such instances can cooperate together at the edge level, and we can leverage, for example, OpenFast-based orchestration that support multi-node deployment. So we can also have this kind of processing that involve different nodes that can cooperate in the local area network. When workload spikes or a task exceeds, I'll say, edge capacity, we can offload to cloud. So we have the cloud burst capabilities. which can offload heavy workload to the cloud. For example, we want to implement multi-class ECG classification by means of models that employ the use of transformers or attention-based mechanisms. In this kind of problem, in this kind of case, we can leverage cloud, for example, Amazon Web Services, to implement the same function, but with a more accurate algorithm. So this creates a unified edge cloud continuum, which is the objective of our project. And we have the edge first section for responsiveness, privacy, and autonomous operation. We have the cloud bus section for elasticity, scalability, and advanced analytics. This kind of approach is adaptable from single room monitoring to full hospital scales infrastructures. We also included within this hub a privacy preserving rapid voice assistant, which can support fully offline spoken interaction for alert queries or system updates. As a real scenario, we integrated within this application a commercial available sensor, which is a solution which has been made by a company, an Italian company, Conftec. The solution is called Audai Senior, and it is a wearable medical device which is built into a smart garment. It is designed for continuous non-invasive real-time monitoring of adults. It can measure heart rate, real-time ECG, breath rate, and body position by means of an accelerometer and movement. So all these things are supported with usage of textile sensors that are woven into the garment. The standard solution includes a sensorized garment, a small electric unit, and a mobile Audai app mobile application for viewing real-time data and generate report. As a department, we signed an NDA with this company because we wanted to have access to raw data, so we developed our own lightweight middleware Android application. And thanks to this application, we are able to capture the raw signals from the microcontroller. The microcontroller sends information and data to our mobile application, and our mobile application can communicate by means of the MQTT protocol with the Entrust Hub. So how we implemented the edge first processing. Once data arrives to the Raspberry Pi based Entrust Hub, we can perform local anomaly classification by means of containerized fuzz modules. This edge first strategy ensures low latency and privacy with immediate feedback on ECG or movement abnormalities. I want to stress that this solution can retain full autonomous operation because we implemented a set of services at the local layer, okay? But we can leverage the MQTT-based local data pipeline thanks to our MQTT broker, which is local. When more complex analysis is required, for example, multi-class ECG classification, our hub can bus to the cloud, offloading to AWS for deeper processing. Currently, the system also supports glucose level reporting, but not via certified continuous glucose monitor because we were not able to retrieve medical sensors, medical certified sensors, but we can provide the glucose readings via voice input at moment. So this hybrid model combines responsiveness, privacy, and scalability in a single health monitoring solution. As key takeaways, I would like to say that we are still in the phase that we are experimenting the Entrust Hub. The project has not finished yet, but the Entrust Hub is proving to be an effective edge-first cloud-based architecture for real-time health monitoring. We were able to integrate commercially available certified medical grade sensors. We are able to give local analytics, ensuring low latency private anomaly detection directly on the Raspberry Pi. We are able to offload requests to AWS service in case we require more accurate models to be employed. And the modular and container-based design enables easy deployment from single rooms to full hospital environments. Of course, there are many future directions for this work. We would like to expand sensor support, including, for example, additional wearable biomedical devices. Doctors are not inclined to use non-certified sensors, so there is a very important, how to say, problem in sourcing certified sensors that allow direct access to raw data for the analysis. We want also to explore adaptive model selection to improve performance of data deep learning pipelines across heterogeneous edge hardware. And we would like also to explore context awareness by including, for example, environmental data, because the system is capable of accepting such data by means of standard protocols. Of course, we can explore multi-node orchestration in hospital settings through OpenFaaS for distributing parallel processing. Okay, I think it's enough for me. Thank you for your attention. I will leave the stage to the next speaker. Thank you.
Thank you, Luca. We will have the question time at the end, so I will immediately pass the floor to Dr. Raffaele Gravina.
All right, so first of all, let me also thank Claudio to lead this very interesting webinar and for inviting me to join this nice opportunity. As introduced by Claudio, I will present some of our current research by means of funded project within the same funding scheme of Entrust. So it's a national project that funds fundamental research. The project here representing is CocoWares, which has the main objective to define and implement a framework for supporting continuum computing in wearable systems in particular. Okay. Since Claudio already introduced me, I will just skip this slide also for the sake of time. So we are actually living today in a wearable world. Many of our accessories and clothes are actually already augmented with technology, with ICT capabilities. For example, notably smartwatches, which are wearable devices, are augmented with many electronics in terms of sensors, user interfaces through displays, and computation capabilities. But there are a wide plethora of devices that can be worn potentially for long term, virtually 24/7. This market shift is being pushed by the ever increasing interest of fashion firms like Ray-Ban or even the Levi's, famous jeans firm. let's say, build up partnership with tech companies such as Meta, Facebook, or Google. Wearables are not just accessory, but as also introduced by the previous speakers with the use case, also garments and clothes. So it is relevant to face some of the open challenges that are intrinsically related with this technology that is going to be more and more diffused into our daily life at global level. So there are some distinctive features related to the wearable computing systems. As we already said, augmentation is one of the key elements. Wearable systems allows or potentially allows to augment user perception, to improve cognitive capabilities, such as, for example, augmented situation awareness. They support intelligent smart behavior. So not only they can collect physiological or behavioral signals from the user, but also can provide insights out of those data, so extract information and eventually gather knowledge, high-level knowledge out of those raw data that are initially collected. They are, or they aim to be non-invasive, which in fact is an important driving factor for user acceptance, as long as they are, let's say, hidden within actual daily life accessories such as smart glasses or even rings. They will more and more easily accepted by the users. And another key features is that they have the clear potential, which is at the same time both good and bad thing, to capture very personal sensitive data, of course. The point here is that they are not just sensors. These devices can, of course, collect, as said, physiological measures. And so, yes, they are equipped with sensors, but they are indeed much more than that. This is a very simplified but still up-to-date architecture of a wearable device. Just without going into details, but the audience might recognize that this indeed is a micro PC. The architecture respect or is compliant with the von Neumann machine. So yes, there are sensors, but there is a processing unit. So computation can be enabled on device. And unfortunately, as it stands, we have to admit that in most cases, this computational power is way underexploited. In fact, in most cases, those devices are basically used as dummy wireless sensors, so that they stream raw data without relevant, or in some cases without computation at all, on the radio interface. So the aim of our CocoWare project is to exploit as much as possible the computational capabilities of those technologies, and actually to even augment and extend the capabilities that are potentially that can be potentially provided to the application services. So of course there are stringent requirements and constraints we have to deal with. In many cases, the services that the application services that runs on those systems are at least near real-time sensitive. So the timing issues is a real problem that must be faced. As Dr. Greco anticipated, there is an issue related to the context awareness. Many of those systems cannot actually work into sandboxes in let's say full isolation, but their behavior depend or should also depend on the current context they are operating, the environment in which they are operating. Of course, as we said, privacy is also a concern because the signals that they are potentially able to collect are extremely sensitive. So this is also an important dimension. It should be taken into account. So the project, CocoWare project, has three main pillars. Actually, I forgot to mention that it is a small national project with three partners from the academic world. The University of Calabria, with me as national coordinator, is the let's say leading institution, but we have also the pressure support of the other two research units, which are the University of Bari and the High Performance Computation Center of the National Research Council as third partner. The project has these three main pillars with complementary expertise from the consortium of theoretical foundation, as we will try to briefly introduce. There is a strong dimension of AI and machine learning algorithm. And as said, there is not only to design the framework, but also to provide practical prototype. Actually, the project is already in open source. We have an open repository, so for the community that may be interesting to contribute, why not? There is a GitHub project with all the source code, and I think also some of our data sets collected by our use case that is freely available. So the core of the idea is that there is a priori and, let me say, arbitrary assumption that some of the computation is enabled by default in software. Most of the computation is enabled in software, while only certain typically low-level functionalities are implemented in hardware. But this is actually an arbitrary design choice, which, as a matter of fact, limits the full exploitation of these systems and the application services that can be implemented atop of them. So our idea is to let's say recapitalize the knowledge that let's say take its roots in the embedded system design of a methodology that is an hardware software co-design methodology, also known as platform-based design, where basically the decision of what has to be implemented in software and what is going to be implemented in hardware, it is actually the result of an let's say systematic solution of a problem, which is the definition of the platform. So the architecture of our system at its highest abstraction layer does not distinguish between hardware and software elements. So in CocoWare, we are defining platforms, components, let's say elements of the mechanism that are eventually exploited by the application through both software and hardware building blocks. We exploit this through hardware programmable logic, therefore FPGA chips. There exist already in the market already now FPGA chips that are usable in wearable systems. To the best of our knowledge, that there exists no commercial solution that exploits FPGA chips on wearable devices, but there are FPGA chips that already now meets in terms of energy requirements, even from an economic budget point of view, meets the requirements of most of the, let's say, mass market wearable tech. So the project is still ongoing. We have already open sourced, as I anticipated, several building blocks of the framework. We are working on the let's say mechanism that allows the automatic or semi-automatic, it's better to say, design, let's say, support for the best selection of hardware or software implementation of a given function according to certain user or, let's say, designer selectable optimization metrics. So we are designing a tool that allows the designer to select by priorities given metrics, for example, energy consumption or computation performance, and at the same time also to select constraints. For example, the economic cost and other relevant constraints, such as physical dimension. So also physical constraints are important. As we said, there is a non-invasive, let's say, dimension that is important. And so the idea is to allow the tool enabled by machine learning intervention to provide an exploration of the design space in a way that before it was not possible to be done. The traditional hardware software co-design is based on standard optimization problems. So you have typically linear optimization problems. You have a cost function subject to constraints. So the solution is typically, depending on the complexity of the problem, carried out by analytically or by approximation. So we are introducing this idea of exploiting modern AI or machine learning techniques to explore the solution space with this novel approach. I think I have almost used all of my time, so I will just go through the use case very quickly. In order to exploit, experiment the current results of the project, we have implemented an indoor localization system, wearable systems that are potentially allows to localize and track users, but in general, let's say mobile objects into an indoor environment through ultra wideband radio. So we have two alternative implementation. One that is based on microcontrollers. In this figure here you see an ESP32 that is programmable in software. It's a microcontroller that can be programmable in software, and another alternative implementation based on FPGA chips. So we basically implemented the full pipeline, including the machine learning algorithm that we used. We have two alternative implementation. One is based on the popular KNN, and another on decision tree. So all the processing pipeline, from the feature extraction to the signal conditioning up to the classification is enabled through reusable components. We provide both the software and hardware implementation of those components, and the designer can select which of those components has to be used in a transparent way. So basically, the designer deal with interfaces. So the actual implementation that can be software or hardware is enabled by let's say a design choice. So the designer select the top priority metric that has to be optimized, and right now, through a semi-automatic, let's say, support that is not open sourced yet, the framework allows to, let's say, provide a potential solution to the designer, as some of those let's say functionalities, computation can be implemented in hardware, and some others in software. This is the FPGA board. On the board there is the FPGA chip. Of course, this is not wearable per se, but the chip itself, it is potentially can be integrated into for size and energy, let's say, budget, integrable into wearable systems. This is a breakdown of the FPGA resources that we are using for the use case. So what you are looking here is the KNN and all the other computation, let's say, that is implemented in hardware on the FPGA chips that we are using. Of course, you have the possibility to measure the several relevant metrics, the energy expenditure, and the actual execution time. That is also an important metric. So you can compare in order to better select, the best or the most suitable implementation. You can explore these metrics and consider the overall execution time or the energy consumption as constraints, and verify if your implementation proposal meets these the requirements that you are setting or not. We also are let's say studying the accuracy differences, because the FPGA implementation has to, let's say, trade some of the resolution and accuracy with, let's say, practical implementation possibility. But the accuracy difference between a pure software solution that is implemented on microcontrollers is limited, so way less than 1% error difference with respect to a pure solution. It is a live project. We are still working on this. So if you are interested to get in touch with us, to play with the open source that we have, please feel free to reach me. I will be happy to guide through the current results. So thanks again, and yeah, looking forward for Q&A.
So thank you also to Dr. Gravina. I think that we can open the question time, and I would like to start with a first question that it is general purpose, so I will reply to it. But in the meantime, I would ask to the two speakers to take a look to the question and answer boxes and read the second question. So the first question that we have received is about the terminology, and in particular, Dr. Memis asked which could be the better nomenclature for the domain and the solution we have discussed so far. Telemedicine, telehealth, Internet of Medical Things, smart wearables, and so on and so forth. So I think that this is a very nice and important point. As I anticipated during my slide, all of these terms, most of time, are improperly used, and they result as buzzword. What we have discussed so far could be wrapped up under the name of smart healthcare. Why? Because healthcare 4.0 actually refer to a broader umbrella of system-level transformation that are inspired by Industry 4.0 and that are focused to provide the fully integrated and automated healthcare ecosystems. So the perspective is more organizational. On the other part, Internet of Medical Things or healthcare Internet of Things specifically focus on tasks such as continuous monitoring and data acquisition. Okay, so the focus is at the device level, but what we have seen today is an ecosystem in which we have not only IoT. IoT is one of the enabler, but we have also AI. We have also cloud, edge. So with the smart healthcare terms, we intend a broad digital transformation of healthcare that includes a lot of paradigms and that altogether aims at improving the care quality and the efficiency. So not only organizational and not only at the device level for data monitoring. Okay, so this is my my idea, and this is what typically is reported in the literature. After this question, we have received other two. So I would like to ask to the speaker if they would like to reply to the other question.
So I would like to start with the questions from Dr. Raymond. If I understand well, he's referring to how the Continuum operator support in both the projects. In the case of the Entrust architecture, we try to realize the Continuum by trying to implement the same function, the same services at different levels. So if we are at the edge level, we have to implement functions that, for example, provide the anomaly detection phase and can respond timely to the patient with the first grade of accuracy, which is, for example, being certain that you have a normal behavior or an abnormal behavior going on. So you can implement this thing by, for example, training a binary classifier, which has an higher accuracy in detecting the anomalies. If you detect anomalies at the edge level, you can forward the process of analyzing, for example, the WAR data acquisitions to a more accurate, model, which can be hosted at a fog level. For example, if you have fog servers in the proximity, or you can, for example, leverage Amazon Web Services, cloud services that can run much more computational intensive algorithms to have a more accurate, for example, in the kind of a multi-class ECG classification, and you can detect which kind of specific anomaly you have to treat. Okay, I think this could be the answer to the second question. I don't know if Raffaele wants to add something to this.
Yes, what I can add to your reply is that the CocoWare's perspective it's on the opposite, let's say, direction with respect to the usual view of the computing continuum that considers, a layered architecture composed by, the cloud, the edge, sometimes sub layers, smart, far, full-featured edge. We are interested into, let's say, adding a further layer of computation that is the hardware. And even if you consider a programmable logic-based platform, for example, an FPGA-based platform, you can still, in certain application scenario, you can still at runtime decide whether to use a component implementation that is executed in the hardware logic of the chip, or on the software programmable part, because FPGA chips they also have, let's say, a software general purpose unit that can execute software code. So depending on the actual metric that you have to optimize, the selection of the functionality, whether the hardware or the software implementation can be dynamically change. So this choice not necessarily is based on let's say, once at design time, and therefore is, hard coded or written on stone. So therefore, the let's say computing continuum aspects that are usually taken in consideration whether to move or flood your computational task into the different layers of the traditional distributed architecture, from the cloud to the edge, up to the IoT. Is potentially, so the same conceptual problems can be potentially be applied also on the other end, so from the software to the hardware implementation. And again, those can lead to a dynamic configuration change on the application from where the computational task should be executed, whether in software or in hardware.
Thank you. Another question is about the trade-off between security, scalability, and price with respect to cloud-based or edge-based implementation. So Dr. Memis asked which is better. I would like to say that it depends of the cases, and it depends of the actual implementation. So the cloud has its own peculiar benefit. The edge has its own peculiar benefit. Obviously, if you stay at the edge, your data will not travel over the internet, and your implementation could be cheap, but the security is in charge of you. So it depends of how you would like to implement. If it is a, let's say, private system, or if you think to manage an hospital without the cloud, it is different. So one size does not fit all. Both implementation have pros and cons. So it depends. Actually, it depends almost of your ability to implement. Cloud could be cheaper if properly set up, or edge could be cheaper if you are able to select the device and to set up them on premise. So it is quite hard. It should be evaluated case by case, the security level and the price that you could achieve in your systems. So it is almost impossible to say all the time is better cloud, or all the time is better the edge. So I hope that I've replied to this question. If there are other questions, otherwise I think I see no other question in the buffer.
Yes, I can confirm that we do not have any further questions so far. Oh yes, we have final one in a question box.
So do we need to run our machine learning model in embedded system or edge device? Yes, it could be containerized, or you can develop it on your device. It depends, again, for example, of the accuracy level you would like to achieve. So for some, if you think, for example, about video processing, maybe it should be a bit hard to implement on a Raspberry, but if you have other kind of devices or embedded system, such as GPU-equipped devices like Google Coral, then it could be suitable. Otherwise, if you don't want to spend money in expensive devices, you could think of container, so that you can also move it It depends. The good thing is that the technology pose no barriers. So your solution could be twinned and mirrored at the edge or at the cloud. So that's the good news. Technology improvement allow us to create and to mirror solution both at the edge and cloud. But it depends obviously of the performance you would like to have.
Okay, so if we do not have any further questions, I would like to thank you for your valuable presentations and for time that you involved in today's webinar. Also, I would like to thank the audience for joining this session and these webinars, the Sensors webinars. As a reminder, the recording will be available as soon as possible on our SciForum platform. And please feel free to join us again on upcoming webinars as well. Dr. Savaglio, you can conclude this meeting and close this webinar.
Yes, so thank you also by my side. Thank you for your attending, for your attendance. Thank you for both speakers, and I hope you have enjoyed it and take some pills of these research projects. It has been a pleasure to me to chair this webinar. I hope you enjoyed.
Bye. See you again. Have a nice day.
Thanks.
Thank you, Tayana. Bye.
Bye.
Enjoy.
Goodbye.